In your study of parallelograms, you learned some additional properties of these figures. One particular property involves two diagonals. Can anyone recall what this property is?
Miss, I think it says that the two diagonals of a parallelogram bisect each other.
Yes, that is right. Is the converse also true?
Converse? Is that what you get when you interchange the hypothesis and the conclusion of a statement?
Yes, that's correct. You can give the converse of this theorem.
Let's see. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram.
We will use this property to solve the next problem. How do we use the midpoint formula to show that the diagonals bisect each other?
We can show that the diagonals have the same midpoint. Can I try it, ma'am?
Go ahead, Doms.
The computations show that the two diagonals have the same midpoint. Thus, the diagonals bisect each other, and ABCD is a parallelogram.
Very good, Doms. Class, this problem and the ones before it show us that the midpoint formula has many applications in mathematics. So you must remember it because you're likely to encounter it again.
Miss Michelle, is it possible to find similar formulas that will allow us to determine other points in a line segment? For example, can we find the coordinates of a point on a line segment AB which is twice as far from A as it is from B?
That's a very good question, Doms. In fact, our next topic is exactly about this theme. We will now extend the midpoint formula by considering other subdivisions of a line segment. Consider the following. Let AB be a line segment and let P be a point on AB, such that the ratio of the length AP to BP is R1 is to R2. Find the coordinates of P. Let A be the point x sub 1, y sub 1, and B be the point x sub 2, y sub 2. As before, we draw horizontal and vertical line segments through A, P, and B to form right triangles AQP and PRB. What are the coordinates of Q and R?
Point Q is the intersection of the horizontal segment AQ and the vertical segment PQ. So Q has coordinates x and y sub 1.
Similarly, R is the intersection of PR and BR. So we have point R with coordinates x sub 2 and y.
From our given figures, how are these two triangles related?
They don't seem to be congruent, since triangle AQP looks smaller than triangle PRB, but they seem to have the same shape.
Do you remember what we call triangles having the same shape?
I think we refer to them as similar triangles.
That is correct. Do you remember the characteristics of similar triangles?
I know that the corresponding angles are congruent.
The corresponding sides are proportional.
Yes, I'm glad you remember. Do you remember how we can show that two triangles are similar?
Is it ASA? No, that's for congruence.
We have the SSS and AAA similarity theorems.
Which of these can we use here?
The vertical lines are still parallel, and so are the horizontal lines. Then the corresponding angles are congruent.
Which angles are these?
Angle PAQ is congruent to angle BPR, and angle APQ is congruent to angle PBR, since they are pairs of corresponding angles formed by parallel lines cut by a transversal.
Angle Q is congruent to angle R since they are both right angles. This means that the two triangles are similar by AAA similarity.
Yes, that's right. So now the triangles APQ and PBR are similar. What do we know about their corresponding sides?
The corresponding sides are proportional.
How would you express this proportion?
The ratio of the values of AP and PB is equal to the ratios of AQ and PR and to the ratios of PQ and PR.
From our figure, can you determine the common value of these three ratios?
Since the ratio of AP to PB is R1 is to R2, this must also be the value of the other two ratios.
Yes, very good. We will now use these ratios to determine the coordinates of P. As before, we will write P with coordinates x and y, recalling what we did to get the coordinates of the midpoint. Can you suggest how we can get the coordinates of the point P?
Since the triangles were congruent, we equated the length of the corresponding sides. But now our triangles are no longer congruent, but just similar.
I think we can use the ratios to determine the coordinates of P.
Would you like to show how this is done?
Okay.
Can you explain to the class what you wrote?
The two triangles are similar, so their corresponding sides are proportional. Using the ratio of the horizontal sides, we can algebraically solve for the x-coordinate of P. The length of AQ is x minus x sub 1, while the length of PR is x sub 2 minus x. Thus, the length of AQ over the length of PR is equal to R1 over R2 is equal to x minus x sub 1 all over x sub 2 minus x. And we can use this to solve for x. The y-coordinate can be determined by using the ratio of the vertical sides. The length of PQ is y minus y sub 1, while the length of BR is y sub 2 minus y. The ratio of PQ to BR is R1 is to R2.
Wow, Doms! You're so smart to figure that out. I wish I were as good as you.
I guess I was just lucky to see the similarity with the midpoint problem.
Maurice is right, Toms. That was really good. Now let's use this formula to this problem. Find the coordinates of the point P, which lies on the line segment AB. If P is twice as far from A with coordinates negative 1, 7, as it is from B with coordinates 8, negative 5.
Can I try it?
Go ahead, Danzel.
Since P is twice as far from A as it is from B, we have R1 equals 2 and R2 equals 1. We then substitute the coordinates of A and B and the values of R1 and R2 into the formula to get the coordinates of the point P.
How can we check if the coordinates are correct?
We can compute the distances from P to the endpoints A and B.
Would you like to do that?
Okay. The distance from A to P is 10 units, which is twice its distance from B, which is 5 units.
Well done, Joseph. Our next problem will be assigned as homework. It is a bit different from the problems we have discussed today, but I assure you that it can be solved using the formulas we have derived.